Stuck on CNA labs? Tired of scattered tutorials? This full course covers every exam topic with real lab configs. Grab your free lab in the description. Ready to pass CNA and boost your career? Start now!
Hello, stud. In this lesson, we'll learn about network topologies. In the last lesson, we learned about network devices. Different network devices and different numbers of network devices are connected via our media or our cables to form a mesh-like structure. This structure diagram, can be called a topology diagram. Different requirements and different enterprises will have different network topology diagrams. Here we'll learn some common or classic network architectures. After completing this lesson, you should understand how our network devices should be interconnected. Second, understand different network architectures and their characteristics. This lesson has roughly 3 parts. First, the 3-layer and 2-layer models. Second, the collapsed core model. Actually, the collapsed core model is a variation of the 2-layer model. Third, we'll get to know wide area networks. First, let's learn about the 3-layer and 2-layer models. Before learning the 3-layer and 2-layer models, we first need to learn something. Let's add a knowledge point. It's about layer 2 switches and layer 3 switches. A layer 2 switch. As we say, a switch definitely has switching functions. A layer 2 switch has only switching functions. It only has switching functions. Generally, its role is mainly for end-user access. It also provides some basic access security. Since its functions are relatively simple, its cost is relatively low. Of course, its drawback is having fewer features, and its performance is relatively weaker. For example, the Cisco C2960X. This device is already end of life. It's already a layer 3 switch. Is essentially a switch that, besides switching, also has some routing functions. In other words, you can treat it like a router. It is not just a simple switch. Its main function, generally speaking, is to aggregate traffic and perform high-speed packet forwarding, while also providing routing support. So, a layer 3 switch, compared to a layer 2 switch, has more functions, and its performance is also stronger. That is its advantage. The downside is its relatively higher cost. For example, the C3850. This model is already end of sale. The latest 9000 series, the Catalyst 9000 series switches, are all layer 3 switches. During enterprise network deployment, we cannot simply use layer 3 switches everywhere. Although its performance is great, and it has many features, but because the cost is high, your project might not be able to afford it. Right? The budget might, so we need to budget carefully. Budget carefully. Where to use layer 2 switches and where to use layer 3 switches to minimize our costs as much as possible. Right? In this way, we are more likely to, at the same time, we can maximize the utility of our equipment. Right? Let's learn about these switches first. Because we have layer 3 switches. Therefore, in the enterprise internal network, within the LAN, we no longer need to use routers. So, as we mentioned earlier with switches, I told you before, in our daily work, basically 90% of the devices are switches. Okay. First, let's look at a very classic model. We call this the 3-layer network model. Although it's called 3-layer, actually, we refer to it as 4 layers. Right? From this structure, we can see it really has 4 layers. Okay, so, these 4 layers, we treat this exit layer, the firewall at the exit layer, or the router. This one, we discuss it separately, because this part is the boundary connecting our internal and external networks. its policies and such are actually quite complex. We will cover this later and expand on it so, what we need to learn first is how to build our internal network. First, get the internal, then, we will learn how to connect at the exit point. So, what we mean here by three-layer network model actually refers to our internal network. Just these bottom three layers. These three layers, we call them the access layer, distribution layer, and core layer. Of course, in some places, the distribution layer is also called the aggregation layer. That's just a difference in translation. I actually prefer the term aggregation layer because its most prominent feature is the aggregation of traffic. Let's look at it layer by layer. First, let's look at the access layer. For the access layer, as you can see, the shape of its device icons is different from the device shapes above. In the previous lesson, I told you that devices with these kinds of icons, we call it a layer 2 switch. Called a layer 2 so from the distribution layer to the core, it is a layer 3 switch. A layer 3 switch. Then why at the access? Generally we use this layer 2 access switch. Because at the access layer, its role is relatively simple. At the same time, its traffic volume is also relatively small. Relatively small. The main function of the access layer, as you can probably tell from the name, its main function is user access. You have all kinds of computers below, right? And all kinds of devices. It provides access for them. That is, it provides network ports. Just run a network cable to, of course, in your daily office work. What you see might not be a direct network cable. Instead, you are given a wall jack. Right? You plug a network cable from the wall jack into your device. Actually, it is all the same. The cable connected behind this wall jack, in fact, goes to our access switch. So, in this case, we generally use a layer 2 switch. Always use a layer 2 switch. Why is that? Firstly, because we might have a large number of users. The number of users may, for example, let's say we have or 1,000 computers that need network access. Computers that need, so let's calculate this now. For example, a 24-port gigabit switch. A 24-port gigabit, we will set aside 4 ports. Used for right? Then 20 ports are used to connect our computers. 20 ports are used to connect our computers. So you can calculate this for yourselves. Right? So in this case, 50 units. We need 50 switches. Now, if you are using layer 3 switches, such as Cisco's 9000 series, like the 90, right? The Catalyst 9300 switch. This switch, a single unit, costs at least 15,000. Even the cheapest model, right? If you use layer 2 switches instead, like the 296, right? Of course, that model is all, what you can still, for example, is the 1000 series switches. The C1000, now, it costs around 3, Look at that price gap. For the same 50 units. Look here, you need a budget of 750,000. But in this location, I only need a budget of 100, right? So the price difference is huge. However, actually, even if you use a layer 3 switch, like the Catalyst 90, and deploy it here, you'll also find that, actually, you can't tell the difference. For the user, they really can't tell whether you use a 90 or a Catalyst 1000 series switch. It's all the same, because its role is quite simple. Just receive the traffic sent from your PC. Receive, and then forward it up. Send it out, right? So using a layer 3 switch versus a layer 2 switch makes no difference here. From a performance perspective, our layer 2 switches are already sufficient. Therefore, generally, at the access switch layer, we typically adopt layer 2 switches. Of course, at the access layer, we actually provide one more thing, which is our PO function. Right? In our enterprise campus networks, basically, we deploy wireless networks. APs connect to them. For AP, we typically use SPOTO to power them. This is more convenient. Right? So for access switches, some devices, we will purchase PO models. Purchase PO models. They provide user access, right? Of course, they can also provide access security. For example, against ARP flood attacks. Such behavior, we can prevent it at the access layer. We'll expand on this later in switching security. When we get to it. It can also provide access control. Like in some schools. When your computer connects, you can't just access the internet directly. You must complete identity authentication. Right? Enter a username and password. Then you can connect normally. Right? This function is also implemented at the access layer. So that's a basic overview of our access layer. Moving up from the access layer. This we call north-south direction. Right? North-up. North-south direction. Moving upward. Reaches our distribution layer. Reaches our distribution. The main function of the distribution layer. The most prominent is to aggregate traffic. To aggregate traffic. We just mentioned 1,000 devices. And we have 50 access switches. 50 access switch right here, right? So, at this point, if you directly take a router to connect to the you connect one cable from each switch. One cable to the router. Right? Run a cable to the router. Does the router have that many ports? Certainly, right? There, we need to aggregate the traffic here. Perform an aggregation. Right here, we typically use a layer 3 switch. Meanwhile, its interface speed, compared to our access switch speed, is much higher. General, in current projects, access switches provided here. All gigabit ether, fast Ethernet ports are basically obsolete. It's basically gigabit to the desktop. Right? Gigabit to the desk, okay. So at this point, our aggregation switch. Generally, it's the port that connects to the switch below us. We need reach 10 gigabit. Need to reach, because you will connect below. For this switch, below the switch, I will connect 20 computers. Right? Although not every computer can reach full. Net, right? Because there isn't constant, frequent data exchange. Most of the time, everyone's traffic is actually not that large. Right? It's all, so at this uplink point here, the interface speed should be slightly higher. One tier higher. 10 gigabit, this is a 10 gigabit switch here. 10 gigabit, this way, with one switch, For example, if this is a 24 port switch, from this, I can take out 20 ports. Right? Then I can connect 20 switches below. 20 access switches can be connected here. This side also supports, right, okay, so in this case, well, the 20 hosts below. Okay, and here are 20 hosts connected to one access switch. And then, 20 access switches connect to one aggregation switch. Okay. So in one switch will carry how many users? Well, 400. 400 users. And this device also carries 400 users. But what if we have 1,000 here? And it's not then we add another aggregation switch. Right, add another aggregation switch to connect. Right, the remaining below. How many left? Right, 10 access switches left. Connect here. This can carry traffic for 200 hosts. All concentrated here. Here we can see traffic is aggregated here. Okay. Of course, when we design a network, as a network engineer, you must always keep two words in mind. We call it redundant. What does redundancy mean? Well, it means you need a spare. A backup plan. For example, our switch. Right? As you can see here. It has two cables connecting to our aggregation switch. Why would we operate? Well, because failures can occur in an enterprise network. Sometimes faults just happen. For instance, this cable gets chewed through, or all sorts of weird reasons cause this link to fail. If you only have one uplink, then all users connected below will lose network access. The entire network, right? But if we have two cables, at least I still have one cable working. Right? So if this one I can use this cable for communication. Isn't that right? So this provides some link redundancy. Meanwhile, we must also consider what is device redundancy? For example, this aggregation switch fails. Right? If I don't have a redundant aggregation switch, no redundant aggregation, then the 20 access switches connected below, and the 400 endpoint hosts connected below. Will all the computers lose network access? Right? I don't. So, besides link redundancy, we also need device redundancy. This concept of redundancy will be mentioned repeatedly in our later studies. Meanwhile, at the aggregation layer, since we carry heavy traffic here, and also, usually, this traffic of ours will have different destinations. It has different For example, some traffic is destined for the external network, accessing the some is destined accessing certain resources on our internal network. For example, we have some OA systems, right? Some CRM, some ERP. These operate, these production-related things. And also, they need to communicate with internal colleagues. To communicate with internal, their traffic will be of many types. Right. So at the access and distribution layer here, we will provide routing choices. Routing choices are needed here, meaning we need to operate here. Layer 3 switch. So the number of switches used here is right. And also, we are already using 10 gigabit Ethernet. Right. Generally, 10 gigabit switch are all layer 3 switches. General 10 gigabit switches are all, so these features are all supported. Moving further up is our core layer. The core layer. Its role is actually to provide high-speed forwarding. To provide high-speed, of course, it is also another aggregation of traffic. As we just mentioned. These 1,000 end hosts. Right. 1,000 and here I will have 50 units. And then here I have 3 units. I need 3 access switches here. Right? This is actually manageable. But what if I scale it up tenfold? If I have 10,000 end users to connect? Here I would have 500, and here, for distribute, I would have 30, right? 30, so, I can aggregate the traffic. Once again, here I might only need 2 core switches. Or 3 core switches. This allows us to aggregate traffic once again. Right? Here, 1 core switch can support 5,000 users. Support 5,000, of course, its traffic volume, we might need to use 40G. Or even 100G switches. Or even 100G, to achieve this result. So, in the core layer, it provides high-speed for our data packet, upon reaching the core device. Need fast path selection. Right? After the path is selected. Should they go outward? Or inward? Or what exactly? Right? This place also needs to provide route selection. Okay. So what is this? This is our 3-layer networking model. Yeah, 3-layer So, this 3-layer networking model. In your daily work, when you start working later, this model, you need to use it flexibly. Yeah, you cannot just copy it, right? Cannot copy, no matter what, you just apply these 3 layers. That's definitely, right? What is the most fundamental basis? Right? Based on our customer's requirements. Right. What effect the customer wants to achieve. Then you make adjustments based on that. Right? For example, your core switch might have one last, right? So at this time, connecting like this is also, right? Connecting like this, but you need to explain its problems clearly to the customer. Right? Okay. Okay. So, compared to a layer 3 switch, our layer 2 model, compared to the 3-layer model, our 2-layer model has a simpler structure. Right? Its structure and the required devices the cost will also, note that the cost mentioned here includes not only the device procurement cost, but also the ongoing maintenance cost. Because these enterprise grade require regular maintenance. Right? So if your structure is more complex, the maintenance will be more difficult. And if the design is simpler, the maintenance is definitely easier. Right? So, that's a key feature of the 2-layer model. Features of the 2-layer, it is relative, right? Of course, it has them all. It has them all. Okay. So, next, let's learn about the spine leaf model. The spine leaf model is actually a variation based on the 2-layer model. What's the difference here? These two devices in the middle. We just called the aggregation, or the link between core layer switches. It's gone, right? It's gone. So, the original core in the middle, or aggregation switch, we call this the spine switch here. And the access switches below, we call them leaf switches. Essentially, it's also a 2-layer model. Right? Also a 2-layer model. And this kind of structure, generally, we apply it in data centers. Generally applied in data centers. Compared to the basic 2-layer model we mentioned earlier. In campus networks. In enterprise campus networks. That is, our office network. Right? So, what is the traffic characteristic here? It's predominantly north-south traffic. From your computer, right? To access the internet. This type of traffic is more, while computer to computer. This kind of is actually quite rare. Basically non-existent. Even if you send a message to your colleague, send a file, it actually also goes to. For example, we use TikTok or WeChat. And so, actually, it all needs to be sent to this server, right? For example, to WeChat server, right? And then from this server, it goes to another employee's computer, right? That's the traffic flow. So, in a typical layer 2 environment, in a typical 2-tier model, the main traffic is north-south. It's all north-south traffic. But in the spine leaf model, it's generally applied in our data centers. In data centers, what is its characteristic? It has more east-west traffic. What does east-west mean? Left is west, right? There is more east-west traffic. Because in a data center, we generally don't connect computers at the bottom. They are server, right? Inside, there are many different kinds of various applications. And also, some data storage is located here. Databases, file storage, things like that. They are all here. And then, each of our servers, its role will be different. Some only provide computing, while others provide storage. And some provide some redundancy features, or rather, provide some data processing, and so on. Each server here, its role might be, right? There will be frequent. For example, this needs to communicate with this one. I have files stored on this storage server. And from this storage server, I need to retrieve the, right? So if we use the original two-tier model, with one connect, because in this spot, we have a loop. In this spot, there is actually a loop. There is a loop here. This loop issue, we will explain it. You just need to know that with a loop present, actually, one of these is currently not in use. For example, this loop, within this loop, this path, we are not and within this loop, we don't use this path. Yeah. We don't use these two. So normally I have a server connected down here. And another server connected down here. Right. So what does the data flow look like? It goes to the access switch. Then to the core switch. Then from that core it goes across to right, and then, correct? That's the traffic flow. Traffic on both sides flows this way. Yeah, okay. Now let's look at the access layer. I have a server down here. That needs to read data from a server connected under the other switch. So what does that traffic flow look like? Well, since the link between these two switches is gone, in this scenario, there actually isn't a so-called loop problem. Right. There is no loop here. Every link here can be used normally. Yeah, all can be used so at this, its traffic goes directly to this core switch. And then straight down. Right. Straight down. Yeah. Also, because these links are all working normally. Right. All are working normally. So, it can achieve load balancing. Both paths are used. Right? Traffic is split in. This greatly increases our access bandwidth. It allows two paths to be used for access at the same time. Right? And its cost is relatively low. The cost is if you want to increase this throughput, increase our bandwidth. You just add another switch. Connect it. Right? Then the bandwidth increases again. If all are 10 gigabit, then this part becomes 30, right? Add one more, and it becomes, that is a 40, right? This speed is quite fast. Moreover, the cost is adding a 10 gigabit switch and adding a 40G switch. Their costs are not equivalent. Their costs are not higher end switches. Their prices explode exponentially. It is not simply multiply. So simple. That is to say, here, if I want to extract data from this server below, right, I can access it like this. And like this. Right? I have two paths, and these two paths can be used simultaneously. Bandwidth will double, right? If you have larger bandwidth demands, then you just add more switches. Add more switch, and you can simply and quickly double the network band, double the net. This is fairly simple. Right? Scalability is very good. And also, since it does not need to detour through another core switch. Right? No need to therefore, its latency will also be relative. Latency is also relative. So it is more suitable for environments with heavy east-west traffic. Such an generally, that is our data center. In the data center, this structure is very suitable. Okay. This is our enterprise model. So, what about these models? Generally speaking, if it's a standard enterprise campus network, you should first apply this two-tier model. If the enterprise model is relatively, and the number of users needing is quite large, then at this point, you can consider a three-tier net, because it will aggregate the traffic once more. Right? Okay. This mainly depends on your scale. So, if there is a lot of east-west traffic, right, then at this, we can consider the enterprise model. And remove these two middle links. Of course, in fact, our later learning process, for example, when you reach the NP stage, we can merge these two switches into a single switch. Using virtualization or stacking technology to combine two switches into one. Of course, this is a bit more advanced. We'll cover this when we learn NP. Okay. So, the third topic is our wide area network. What we just discussed is actually how our internal should be connected. Right? So between wide area networks, how should connections be, right? So what is a wide area? Here, I'll give a simple explanation. A so-called wide area network. Its scope is relatively large. Right? So it's called wide. A small internal network of ours. We call it a local area, a local LAN. Right? We call it this LAN can be large or a LAN can be large. Some small ones, like in your home, one router connected to a switch below, then connected to a bunch. Right? This is the most basic campus network like this. This local area network. A bit larger. A slightly larger one. We call it a metro. What I just might be individual home, right? A metropolitan covers thousands of homes. Within a city. Right? Every single home. We use carriers to connect them together and build a network for this city. We call this a MAN. Right? Then we connect city by city. Right? So its scale gets larger and when it grows larger, we can call it a W. At the very beginning, we define WAN. MAN and LAN. Right? For LAN, MAN, and general, we classify them by scale. But at the current stage, this method is not very suitable anymore. Because some networks, some LANs, are actually quite possibly larger than a MAN. Right? So how do we define so generally, we do it this way. A LAN means all internal devices are privately owned. For example, your company. Right? These devices on the switches, routers, APs and AC, these are all procured by you. Install and maintain them yourself. Right? You own all of these. Okay, what about the metropolitan? Well, besides this internal stuff, which what else is there? There is the the service, some equipment from the, but the provider's network is relatively limited. It has a regional characteristic. For example, you can only use it within your city. Right? What about the W? The W, it is formed by individual LANs. Individual, and then, connected into individual ones. Individual metro, and then the are connected together. At this point, our WAN is formed. Our WAN is formed. Its structure is roughly like this. You can take a simple look at this. LAN. It refers to each of our internal networks. Each right? For example, some are right? All internal networks are like this. Then through the ISP. Access, right? ISP access, So the WAN, we also call it an also called a, right? And the LAN, also called an, it is mainly used to connect our different such LAN, or MANs, such remote networks. Its scale is relatively large. Generally, it ranges from tens to thousands of kilometers. It connects many regions and cities. Even countries. Between countries, right? So the largest WAN actually refers to our internet. The internet is currently our largest WAN. The structure is just like this. So, why do we need to learn about WAN? What we just learned. That's its internal network. The LAN, how should I build it? Right? Now, the WAN. After you connect to the ISP, how should you use it? Right? At this point, there are many different structures. Like our point-to-point network. A point-to-point connection. For example, this is our Beijing office. This is our Shanghai branch. Right? At this, between our Beijing and Shanghai offices. Our internal networks need data communication. The internal networks need to, for example, I have a server here. Right? And over at your branch, all the employees there, you need to access this server. All of them need to, right? How can this be achieved? We can use a point-to-point connection. A point-to-point. This connection method. Because it is quite dedicated. Just one-to-one. Right? One-to-one. So its cost is relatively higher. Will be relatively higher. If your number of nodes is not that high. Your sites are not that many. Right? Just 2 sites. Then you can just set up one line to connect them directly. However, if you have quite a few sites, we can then use this method. We call it hub and spoke. Hub and spoke. This hub thing, we've actually seen it a few times already. So, in this, the so-called hub refers to our headquarters. Refers to our head, and spoke refers to our branch nodes. Branch site. For example, this is our head. These are our branch offices in various cities. Right? Hey, in this way, as our company scale grows. In each city, we have opened many branch, the staff inside these branch offices all need to access resources in our head office. Right? For example, chain stores. Chain stores of this kind. Right? Like clothing stores, or food shops, fast food, and so on. Right? Many have their own payment systems, employee management systems, etc. Right? These are all maintained by headquarters. So each of my stores, each remote office node, office network, right, needs to connect to our headquarters. We call this a hub and spoke structure. Isn't it just like the hub we talked about earlier? Right. Over here, it has many ports for you to connect to. You connect each device to this. Hey, one port, right? Isn't that structure very right? This is called hub and spoke. Hub and spoke, yes. Our headquarters node is called the hub device. And the branch node, we call them spoke such a structure. Now, you'll actually find that between our spokes, there are no direct links. There are none between spokes. Of course, we can when we get to the CCIE stage later. Cisco has a proprietary protocol called DNVPN. With this VPN, you can dynamically establish connections between spokes. Dynamically build the connection link. It can be set up and this connection link can also be encrypted. This technology is quite powerful. Of course, that's a bit advanced for now. We'll learn it later in the CCIE stage. We'll revisit it for now, just get a general impression. And then, the most perfect is full mesh. We call it full mesh. Every node has a link to every other node. They all have link. In that case, its cost is definitely the highest. Right? The cost and the number of links is very large. Maintenance is also very difficult. But its redundancy is the best. For example, if this link goes down, right? I can go through here. Or go through here. Right? This gives the best result. But its cost is usually the highest. To achieve this, it might require a more advanced solution. We need to use SD-WAN. Software-defined wide area network, This is also something you'll learn in the CCA stage, Okay, so when these are WAN connections, it can form various logical topologies, It can form this kind of structure, Well, to form such a structure, we definitely need the corresponding WAN links to support it. Right? Well, let's take a when we connect to an ISP, what links are available when interfacing with an ISP, What interfaces or services are available, to use, right? So the most basic one, is broadband, right? I'm sure everyone has this PPPoE dial-up. PPPoE dial-up, It encapsulates our PPP, Ethernet data frames, inside the PPP protocol, So it's called PPPoE, right? OE means over Ethernet. It takes PPP packets, encapsulates them, takes the Ethernet packets and encapsulates them in PPP. Right? Well, generally speaking, it uses a PON network for transmission, PON stands for Passive Optical Network, For example, you can take a look at the optical modem at your home. Flip the optical modem. You can see something called GPON. Of course, some students might have EPON at home. That may vary. Some students might have some might have EPON. Whether they are all PON networks. This network's characteristic. Is that the cost is relatively low. The cost is relatively, and then, generally, its upstream and downstream are asymmetric. If you want symmetry, you need the latest PON technology. It's called XGS-PON. This technology provides 10 gigabit connectivity. Provides 10 gigabit, for example, your home bandwidth right now hasn't reached 10 gigabit yet. So, this technology is currently still quite distant for most people. Still, it is a relatively new technology. Currently, these two are the most used. Even XGPON is rarely used. XGPON is used in but its upstream and downstream are asymmetric. XGS-PON upstream and downstream are symmetric. Both can reach 10 gigabit. Okay. Here, its low cost is mainly reflected in its optical splitting. Reflected in its optical splitting. From the telecom central office, we have a device called an OLT. It used to build this PON network. It is used for the transport network. After it comes out, it will be split optically. What does optical split? Now we all use optical fiber for broadband access. Right? Optical uses light to transmit signals. Here we use an optical splitter. Use an optical splitter to divide the light into several branches. Divide it, then each light path individually serves our users. For example, we split one light signal into 32 portions. Split it into 32 parts. In this, I can connect 32 users downstream. Right? 32, of course, sometimes it's not just one level of splitting. I might split multiple. I split one level, then another level. Then, connect further downstream. Here, for example, I split 132. Then, here I split 1/3. This also depends on whether the optical power is sufficient. Is the optical power right? So in one port on the OLT I can directly serve 32 times 32 users. A quick calculation gives about 900 plus. Right? 30 times 30 is 900. Right? It can provide network access for over 900 households. So its cost is relatively low. And the entire transmission in between. The entire transmission requires no electricity. It's all just a beam of light coming out directly. And here it's physically split with a prism. And split again with a prism here. Letting the light connect to everyone's optical modem. We call this optical modem an ONU professionally. Called an O, connected to the ON, right? Then you supply power to, and it starts running. Right, then you dial up. And you are connected. Precisely due to this characteristic of optical splitting. So actually, in the upstream direction. Especially with everyone's upload traffic. The time you get per second is just 1/32 of a second? 1/32. So, you've clearly subscribed to the gig, right? But your upload speed can't actually reach a gigabit. Basically you have to divide by, do the math, it's about 50 or 60 megabits. Pretty much like that. Right, it is precisely due to this characteristic of the PON. With PON, its cost will be relatively low. Everyone's broadband price will be relatively cheap. Everyone can afford it. If we didn't use optical splitting technology like this, the price of one broadband line, now it might cost per month maybe 1,000 U. Right, but by then, maybe, if we didn't use PON, then we would be paying per month maybe over 30,000 a year. Think about it right, this cost is very high. Not every household could afford it. This is our broadband access. Broadband access, and broadband, is further divided into business broadband and home broadband. Home broadband means it has more split users. Right, all 32 ports might be, all of them might be, right, then this business broadband. Generally speaking, it is in our In the office buildings. Office buildings use this kind of business broadband. The price is relatively high. Of course. One OLT connects to this fiber for optical splitting, which splits fewer connections on this side. So the upstream bandwidth is relatively large. The upstream bandwidth is quite large. Of course, there are other differences. For example, business broadband supports static IP addresses. So your IP address doesn't keep changing. You can run some service-related things. Of course, you need to, but that's a digression. Then, after access, we are actually connected to the metro network. Already connected to the metro network. But this metro network is generally a public network. If you are in a city and you have a building and another building there, you want to connect these two buildings. Between these two buildings for their internal data communication. Right? Through the metro network in between. In that case, you can directly order a metro network dedicated line. The ISP provides access for you at this location, connects to their equipment, and then pulls another cable from there to your other office building. Right? And for this line, generally, if we want a higher level one, we use a dedicated line. Right? Only for your exclusive use. Only for your exclusive use. In this way, our overall bandwidth will be relatively large. However, because it's for a metro, for example, this building is in another, right? Then there's no way to connect. No way to connect. Or even farther, right? So this metro network connection won't work. Won't work. At this point, we may need to use a third technology called MPLS dedicated. The MPLS dedicated line relies on our carriers' existing backbone network, such as China Telecom, China Unicom, or China Mobile. Right? It has a nationwide. Such a this already exists. And then, using label switching technology. This is also an IE level technology. To forward our data packets. In this way, we can use this already established network. Everyone needs internet access. Right? They all have telecom and China Unicom's room lines. Right? Utilize these lines to forward the data. To forward data. While also isolating the data. This data can be isolated. In this way, its cost is relatively higher. The cost is relatively much lower. Each one. This MPLS line. For example, this one is in Beijing. This one is in Shanghai. Right. You can order one MPLS VPN line. MPLS VPN line. It can connect the two sites. For you. Logically, they are directly connected. The problem is, if, in Beijing, right, in the north, you might, a China and in Shanghai, you might have a China, then you need to cross carriers to communicate. This might, much harder to implement. Okay. Also, VPN tech, MPLS is actually, essentially, also a VPN technology, but not as prominent. Because this MPLS VPN line is configured by the carrier, set up by the carrier, you just pay the bill. They will drop a cable free, then you can configure the IP, right, and add the route to it. This is relatively simple. No need to maintain it. But what we mentioned here, the fourth VPN technology, is a virtual private network, right? This one is built on top of an existing, our PPP, right? I already have public IP. After you already have a public IP address, on this basis, you can build. It's logical to build. In that case, there is no extra cost. There is basically no extra cost. Because you already have the broadband anyway. Right? Then, on our devices. For example, on our, we configure a right? On the peer side. For example, on another site. Right? Say, in Beijing, on the router in Beijing. We also configure, then the two sites connect together, and the VPN is up, right? There's no other cost involved. So its cost is the lowest. But, it requires technical, even if you still have to pay. To let our network engineers, or buy a service. Our integrators will configure these things for you. Configure these, and there's regular and also, its stability is relatively poor. It will be affected by your traffic. For example, if an is downloading video, saturating your complete, at this time, your will become and also during internet peak hours. For example, in the evening, from 6 to 9, everyone is online. The internal networks, also have heavy, at this time. This traffic of may be affected to some extent, meaning the quality might not be great. For example, high late, or even packet loss sometimes. The VPN link might even, stability will be, after all, you are getting it for free. It's free, so you also need to check for self-parking. Okay. So these types. Are our WAN links. Now, as for bare fiber. Ordinary people can't afford it. Ordinary people can't afford it. What is bare fiber? The carrier provides a fiber link to us, in between. It goes through no switches or routers. It only goes to its patch panel. Or the fiber patch cord here. This is where the line connection is made. There are no active devices in between. Meaning no equipment that needs power. In between, it's all fiber all the way. It's all fiber all, and then, it reaches your other node. It reaches your carriers. You can think of it as, for example, from Beijing to Shanghai. What about, they just lay a fiber. Running from Beijing, one end connects to your building in Beijing. The other end connects to your building in Shanghai. This is called dark fiber. The cost is extremely high. But its latency is the lowest. Bandwidth is also, stability is, security is the best, but the price is very expensive. The price is very, a student says. Then what if, for example, my home is close to the company. Can I just run a fiber from the company to my home? And use it like, is that okay? It works too. However, this is an illegal act. Because deploying this kind of fiber optic cable requires an ISP license. Running cables without a license. This is actually illegal. It's quite, if two buildings are like your next door neighbor. It's only about 10 or 20 meters apart. So pulling a cable isn't a big deal. But if you need to, cover a much longer distance. Maybe several kilometers. Then this solution won't, okay. So, in this we've roughly covered these points. We learned a few things in this lesson. The first is the three-tier network model. Its character, the access layer, distribution layer, their features, and then, the two-tier network model. It merges the distribution and core layers. And then, the spine leaf model. It's suitable for environments with heavy east-west traffic. And also, some WAN links. That's what we covered in this lesson.